All right. On this video, I'm going to solve some problems for you from Appendix A and Appendix C. We'll begin with Appendix A. I'm going to pick a selection of problems to work on. I'll begin with problem number 7. Problem 7 is the absolute value of x plus 1. And it tells us to rewrite this without using the absolute value. We want that to be just an expression without an absolute value. Now, how are we going to approach this? Well, to do that, we're going to have to utilize the definition of the absolute value. We may be familiar with the definition, we may not be familiar with the definition, but in a calculus class, we have to be familiar with the definition of the absolute value. The definition of the absolute value, when we see it the first time, might be a little confusing. It says, if you're taking the absolute value of A, and if the expression inside the absolute value symbol, A, is positive or 0, then all you do is copy it down without the absolute value symbol. All right, that's our rule. But it has two parts, right? I've written a piecewise defined function here. It also says, if what you find inside is negative, well, you don't just write that down. You write down the opposite of that. Now, let's just take a sidebar here for a second and see how this ties into what we were taught in elementary school. We were taught the absolute value of 2 equals. And originally, we were taught these steps, but we have perhaps forgotten those steps. But what we as calculus students need to do is reintroduce ourselves to these steps. So we need to immediately look at this number, this value, this expression, and say, is this greater than 0? 2 is greater than or equal to 0. That's a true statement. So we use this part of the definition of the absolute value, because what we have inside is greater than or equal to 0. So the definition says, ignore the bottom half, just do this. So our definition says to eliminate the absolute value symbol, we just write down the value we see inside. So the answer to that is 2. And that's what we did all through elementary school and junior high and high school. Now, what happens if they put a negative value inside? Well, we immediately then observe that -3 is less than 0. That means we're not discussing this version, we're discussing this version. Our value inside is less than 0, it's negative. So our answer is the opposite of what we find inside. Now, most of us have forgotten this step, and that's normal. But when we get to a calculus class, we need this step. We need to reintroduce to ourselves the idea that if what we find inside is negative, we copy down the opposite of what we saw inside. Now, what you and I typically do is we see a -3 and we write a +3. That's correct. But why are we doing that? We're doing that because the opposite of -3 is +3. So these are the steps they want us to use to rewrite this expression. This is our A. So we're going to rewrite this definition, and we're going to write it using x plus 1 everywhere we have an A in the definition. So we know the absolute value of x plus 1 is going to equal one of two things. First of all, if x plus 1 is greater than or equal to 0, and we don't know the value of x could be 12. All right, 12 plus 1 is 13, greater than or equal to 0. If that's the case, we simply get x plus 1. But x could be -5. We don't know the value of x. So if x plus 1 is less than 0, our answer is not x plus 1. It's the opposite of x plus 1. Now, we can do some arithmetic here and simplify this. We could formally express this or clean it up a bit. We could say the absolute value of x plus 1, well, it's one of two things. It's x plus 1 if, and here we move the 1 over and we get x is greater than or equal to -1. Okay, we're just solving the inequality. Here we get -x minus 1, distributing the negative sign. If, and we clean this up, we move the -1 over here, x is less than -1. Now, this explains why, when we draw the graph of this, right, back in pre-calc or algebra 2, when they asked us to draw the graph of this, we were taught real quick, well, this is +1. The reason it's +1 is it's -1. And so we move to the left 1, and our slope is 1 from there. And so the graph of this is two 45-degree lines that look like this, and this is -1. And they taught us, if this was +7, it moves up 7. If it's -7, it moves down 7. But we had to learn that if it's +1, we move left. Inside the function, if it's plus, we move left. Inside the function, if it's minus, we move right. And this was our graph. Now, why is this actually the graph? Well, because if we look over here at what we've written for the expression of x plus 1, we have two lines. This line has a slope of 1, a y-intercept of 1, right? That's what this number is. This goes back to our friend y equals mx plus b. This is our y-intercept. Our y-intercept here is 1. So that's here. Our slope is 1. So that line is right here. Right? This is the line y equals x plus 1 from back in algebra 1. But it says right here, we only want that line when x is greater than or equal to -1. -1 is here. So we only want the part of the line where x is greater than or equal to -1. So we get this piece over here. But we're not done with the graph, right? We're not done. We also have this. This has a y-intercept of -1. That's here. A slope of -1. That line is right here. But we only want that line when x is less than -1. If we look here, this x is x equals 0, this x is x equals 1, this x is x equals 2. We don't want any of these x's. And that's where the graph of the absolute value comes from. It's two lines with a conditional, and we get that from the definition. That's what they're trying to teach us in problem 7. Not moving symbols, not memorizing definitions, thinking about what the definition says and what it means. All right, so that's how you do problem 7, and all of those problems where it says rewrite the expression using the absolute value or eliminating the absolute value. We're going to use this definition. You're going to take whatever they put inside the absolute value symbol, and you're going to put it in place of A. All right, let's move on. So that was question 7. So let's take a look down below. Solve the inequality in terms of intervals and illustrate the solution set on the real line. Now, these are just our straight up algebra problem from back when we were in algebra 2, right? So if I pick one of these, I'll pick something like number 17. I'm going to stay away from the linear ones. Here we have x minus 1 times x minus 2 is greater than 0. All right, I stayed away from the linear ones because we talked about those in class. Here, they want us to solve this inequality. And we may or may not remember how to solve quadratic inequalities. But there's a couple of things we need to know. There's a long way and a short way to do this. We're going to stay away from the long way. But the long way says this. Well, I'm going to write it out. Don't do it like this. I'm using this as an illustration to show you how this works. This says greater than 0. These are two factors multiplied together. The only way we get a positive product is if we multiply two positive numbers together, or we multiply two negative numbers together, right? If we take a positive times a positive, we get a positive. If we take a negative times a negative, we get a positive. So one way we could solve this, we could put our or right here, and we could say this has to be positive. X minus 1 has to be positive. And at the same time, there's those prepositions from algebra, x minus 2 has to be positive. Now we can solve these inequalities, right? These inequalities are not overwhelmingly difficult. This says x has to be greater than 1 and x has to be greater than 2. Now we were taught in Algebra 2 how to graph this, right? They told us to make a number line. If we're going to graph x is greater than 1, here's 1. Greater than without an equal sign is an open interval, and we go this way. This is and, not or, and. Here's 2. X is also greater than 2, so we get an open interval there, and we go this way. And means overlap or intersection. So our teacher told us, where are both of those inequalities satisfied? After all, the preposition is and. Where are they both satisfied? They are both satisfied from 2 on, right? 1.5, which sits right here, 1.5, is greater than 1, but is not greater than 2. So that is not in our solution set. So our answer here turns out to be x is greater than 2, which we can write as an open interval at 2, right? Open at 2 because it's not equal to 2 to infinity. But we're not done. We still have to take into account the case where they're both negative, because two negatives multiply together and make a positive. So here we would then start all over. We would say x minus 1 is less than 0, and x minus 2 is less than 0. This gets me x is less than 1, and x is less than 2. And we would again draw our number line. We would graph this. X is less than 1. Here's 1. We're less than 1, so we're going this way. Again, open because it's less than. This says x is less than 2. Here's 2. We're going this way. And we need an and, which is an overlap or an intersection. And so we would end up with, where do they overlap? X is less than 1. And that gives us the interval negative infinity to 1, open at 1. Now this is or, the preposition, so it's this or this. We would represent that as negative infinity to 1. Union means or, 2 to infinity. Okay, that's our algebraic methodology for solving this problem. But that's not the only way we know how to solve it. In fact, this is the longest, most burdensome way we know how to solve this. We could solve this, and I would suggest as a calculus student, we want to know this. This has to be something we're capable of doing, but we want to also be able to adapt, right? We want to be able to look at these problems, understand what we're being asked, and perhaps solve them another way. Now, there's a different technique. And that technique says, okay, what are the x-intercepts? When does this equal 0? Now we know the intercepts are x equals 1 and x equals 2, right? We said, how did I get that? I set it equal to 0, and I know 0 times something equals 0, something times 0 equals 0. So I solved x minus 1 equals 0 and got that. I solved x minus 2 equals 0. So these are my x-intercepts. So one way we can solve this then is we can make a number line. We can put our x-intercepts down here. Here's 1, here's 2. Those are our x-intercepts. We write each factor over here to the left, x minus 1, x minus 2. And now we ask ourselves, what is the value of x minus 1 in this area? What is the value of x minus 1 in this area? And what is the value of x minus 1 in this area? How do I determine that? I pick any number I want from 1 to the left, like 0, for example. I plug 0 in here, I get 0 minus 1. Now that's a negative number, so I'm going to put a negative sign. Now, it would work no matter what number I put in there, right? If I put -7 in here, -7 lives in this region. So -7 minus 1 is -8, that would be negative. Now I move to this region. So I need 1.5, right? That's the easiest number here. 1.5 minus 1, that's positive. So I'm going to put a plus sign, plus. I move to this region, 2 to infinity. Pick a number in there, 10. 10 minus 1 is 9. That's positive, so I'm going to put a plus. Now I go down here. I play the same game with this one, right? Same game. I'll pick 0 again. 0 minus 2 is going to be negative. Here I'm going to pick 1.5 again. 1.5 minus 2. This time that's going to be negative. And then I need a number bigger than 2. I'll pick 10. 10 minus 2, positive. Now, these two factors are multiplied together in our problem, right? This is the technique we use when there's multiplication or division. And then we do what? We simply do this. We say, well, we're multiplying these together. So we multiply these together. Two negatives multiplied together make a positive. So I'm going to put a plus right there in that region. A positive times a negative makes a negative. So I'm going to put a minus sign right there. A positive times a positive makes a positive. So I'm going to put a positive right there. And now I'm done. The question's asking me, when is x minus 1 times x minus 2 positive? Well, it's positive here, and it's positive here. So I can write those two regions down. Negative infinity to 1, union 2 to infinity. And we didn't have to solve any inequalities. The nice thing about this approach, and remember, this only works when you multiply or divide, right? You can't add two negatives and no information. It's when we multiply or divide negatives. But the great thing about this approach is if somebody had asked us this question, we can answer it with our work. Where is it negative? Right there. If they had asked me, where is it negative or less than 0? Sorry, less than or equal to 0. I know it's here, and here, and here. And in Algebra 2, we were taught, that's the closed interval. So the nice thing about this approach, right, this test point approach, is that it answers any question they ask. Now, what happens if they put a 6 over here? Okay? This only works for 0. Well, if they put a 6 over here, move the 6 over here, and get 0 on this side. But this also only works when you can factor the left-hand side. And what happens if you can't factor the left-hand side? After all, I said there were 3 ways to do this. There's another way. Right? That left-hand side, if we were to write that out, that says x squared minus 3x plus 2 is greater than 0, right? That was our original problem. We can graph that parabola. All of us know how to graph that parabola. We know how to graph parabolas. We learned that in Algebra 1, we learned it in Algebra 2. We would find the x-intercepts of the parabola. We know what the x-intercepts of this parabola are. We did the work over here. The x-intercepts are 1 and 2. We all know this parabola opens up because that's a positive number, so it opens up, right? It opens up. We know more about this parabola than just that, though. If you're unaware of the following characteristics of a parabola, when I get done talking about them, stop the video and write these down, right? This is your friend, what we called back in our world, the basic parabola. What we need to know about the basic parabola is not that it starts here and opens up. Yes, those are important facts, but they're not all we need to know. If this is a 1, your parabola goes over 1, up 1, and over 1, up 1. If this is a 1, your parabola goes over 2, up 4. And it goes over 2, up 4. It also goes over 3, up 9, over 4, up 16. This is how the basic parabola works. When you go up over a half, you only go up a fourth, right? Because it's a half squared, so you only go up a fourth. This is why your teacher's parabolas perhaps look better than yours. Well, this is a 1. Right? This is a 1. You know how to find the vertex of this parabola. You have a formula for that. X equals negative b over 2a. Right? That's your formula for the vertex of a parabola from back in Algebra 1. If we plug in our numbers here, that gives us positive 3 over 2 times 1, or 3/2. Our vertex is right here, 3/2. So we know the vertex of our parabola is here. Now we can plug 3/2 in there and figure out where the y value is. We don't really need that because we know our parabola opens up. We can draw the graph of our parabola. Now don't lose the forest for the trees here. We're trying to solve this inequality, right? This is what we're trying to solve. Well, what does this inequality say? It says, when is the parabola positive? Positive means above the x-axis. That's what positive means. Well, if we take a look at this picture, there's where it's above the x-axis. And you know what funny thing about that? That's the point 1 to negative infinity. And that's the point 2 to positive infinity. Right? This is what we need to know how to do. We don't want to just jump into the algebraic symbol manipulation that I did in the first exam, first time I solved this problem. We need to think, and we can do this number line approach. We need to see, and we can do the graphical approach. And if we can do these and develop this kind of problem-solving strategy, then this class is not going to be difficult. It's not about manipulation of symbols. I told you that in class. I'm going to tell you that in every class, because that's how I'm going to convince you that this class is not daunting. It's very approachable and very survivable. All right, so that was number 17. If you look at something like number 23, x cubed is greater than x. Okay. If we want to use the number line technique, we need a 0. So we write this as x cubed minus x is greater than 0. So it's asking us, when is this graph positive? I don't know that graph. Right? You don't know that graph. We know how to draw that graph if we passed our pre-calc class. We don't want to do that. We want to rewrite this, factor out an x. We get x squared minus 1 is greater than 0. That's, right, a difference of two squares. That gives us x minus 1, x plus 1, greater than 0. And off we go to our number line approach. We don't want to use inequalities. Remember the first thing I did on problem number 17? We don't want to do that. How do you multiply three things together and get a positive? Oh, well, that's positive, that's positive, that's positive. Yes. And you're going to have to write three things down, solve them, and see where they overlap. But you know what? This could be negative, this could be negative, this could be positive. Because two negatives times a positive is greater than 0. And you know what's going to happen? You're going to have to write three things down and solve them and see where they overlap. They're not done. This could be negative, this could be positive, and this could be negative. And you know what you're going to have to do? You're going to have to write three things down, solve them, and see where they overlap. But of course, we're not done, because this could be positive, this could be negative, and this could be negative. And you know what you're going to have to do? Yes, you do. You're going to write three things down. You're going to have to solve them and see where they overlap. So you're going to have to solve three inequalities 4 times before you're done if you use that approach. There's got to be a better way, right? And there is, of course there is. We can use the number line approach that you and I talked about just a second ago. We can look for the zeros. 0 here is x equals 0. The 0 here is x equals 1. The 0 here is x equals -1. We draw our number line. We put those points down. 0, 1, -1. We write our factors over here. X minus 1, x plus 1. And we pick our test points and away we go. We pick a number in here, right? -10. Sure. -10, that's just -10. That's going to be negative. Pick a number in here. -0.5. -0.5 is negative. So we put a negative sign there. We pick a number in here. 1/2. Excellent. 1/2 is positive when we plug it in for x. So we put a plus sign. Pick a number in here. 10. 10 is positive. We put a plus sign. Where do we go from here? We play the same game with this. -10 minus 1, negative. -1/2 minus 1, negative. 1/2 minus 1, negative again. 10 minus 1, positive. And we go to here. -10 plus 1, negative. -1/2 plus 1, positive this time. 1/2 plus 1, positive. 10 plus 1, positive. And these are all multiplied together. That's why we're using this technique. Negative times negative times negative is negative. That is not what we're looking for. Negative times negative times positive is positive. That's part of our answer. Positive times negative times positive. Nope, that's negative. That is not part of our answer. Positive times positive times positive is positive. That is part of our answer. And when we draw this or write this down as a list of intervals, we get -infinity to -1, right? This one right here. Open at -1 because it's greater than, not greater than or equal to, union. And, oh, geez, you wanted positive and I did the negative. So I apologize. We get -1. I hear you all yelling at the screen. So we get -1 to 0, union 1 to infinity. And once again, using this technique, no matter what inequality they placed here, we could have answered it with this technique. Now, just because we're working on problem-solving strategies, we could have graphed this. You know how to graph y equals x cubed. You know how to graph y equals x, right? We're supposed to know these graphs. These are graphs we're supposed to know. Y equals x obviously goes like this. It's 45-degree line, goes like this. Y equals x cubed, right? Y equals x cubed. We know it goes through 0, 0. 0 cubed is 0. We know it goes through 1, 1. Right? It goes through here. But it also goes through 2, 8, doesn't it? 2, 8. That's way up here. And it goes through -1, -1. That's right here. But it also goes through -2, -8. The cubic, right? The cubic goes like this. Now, what does this is the question we're focusing on right here, the original question, this one, because we graphed both of them there. What does that say? It says, when is the graph of x cubed bigger than the graph of x? Bigger means above. When is the cubic above the line, right? When does that happen? Well, here's the cubic, it's red. Here, it's above the line, isn't it? It's above the line. This is 1. So from 1 on, it's above the line. We got that. If we look over here, right here, it's above the line. The cubic is above the line. Greater than means above. Graphically, it means when am I above this? Well, we know what this is. This is 1 negative to 0. We have that right here. Multiple problem-solving strategies are the key for our success. All right, okay, so that's problem 23. Now we get down to the right, from there it said do 31 through 41 odd. These are the inequalities that I showed you how to do last night in class. I'm just going to jump on one of these. You know, it doesn't matter which one we pick. They're all going to be the same, except for problem 31, right? Except for problem 31. If we take a swing at problem 31, well, we'll come back to 31. Let's first do something like, 39. 39 says the absolute value of 2x minus 3 is less than or equal to 0.4. And I showed you how to do this in class last night. We're not going to use, or we can, right? You can, but we don't have to use that silly rule in the algebra book. We're going to divide everybody by 2. And when we divide everybody by +2, it doesn't flip the inequality, nothing happens. And now what does this say? This says, here's +3/2, and x is less than 0.2 away from that. Less than or equal to 0.2. Now, 3/2 is 1.5, right? They kind of played, I introduced a decimal, I introduced a fraction, and there's a decimal, but 3/2 is 1.5. And how far are we allowed to go? We're allowed, we can't go any further, right? The distance between these is less than 0.2. So we're going 0.2 this way. We know that's going to be 1.7. And we're going 0.2 this way. We know that's going to be 1.3. 0.2 is all the further we're allowed to go. And now we know our answer. We're not allowed to be, we have to be less than that. So our answer is, and it's equal to, so our answer is 1.3 to 1.7. And we didn't have to solve any inequalities, right? We didn't have to use the definition. If you wanted to use the definition, which we don't want to do, but if you wanted to use the definition, right, then you write negative 0.4 is less than 2x minus 3, less than or equal to 0.4. You move a 3 over here, and that gives you negative 2.7, right? Negative 2.7 is less than or 2.7, 3. Wow. Told you I wasn't good with numbers. Negative 2.6. And then over here, you move it and you get 2x is less than or equal to 3.4. Yeah, I see it. And now you divide everybody by 2 and you get 1.3 is less than or equal to x is less than or equal to 1.7. Same idea, right? Same exact idea. What about number 31? Right? They're messing with us on number 31 because they give us 2 absolute values. Well, the easiest way to do this one, right? The easiest way to do this one is just graph them. Straight up just graph them, right? We'll graph this one in purple. Graph this one in green. So this is going to be y equals the absolute value of x plus 3. This one's going to be y equals the absolute value of 2x plus 1. Okay. Now you know how to graph an absolute value. Go like this, go like this. This one's easy, right? It has a y-intercept of -3 for all the reasons they taught us in Algebra 2 and pre-calc. Has a y-intercept of -3. This is a 1, so it has a slope of 1. So it goes like this, and it goes like this. That's our graph. This is 2x plus 1. We know how to graph 2x plus 1, right? We know how to graph that. We know if we're going to graph this, right? If we're going to graph this, we're going to factor out the 2. It's going to have an x-intercept of -1/2. So that's right here. -1/2. And it's going to have a slope of 2, right? It's going to have a slope of 2. It goes up twice as fast. So instead of going over 1, up 1, which would take it to there, it's going to go over 1, up 2, which would take us up to, we're at a half here. So when we go over 1, up double that, we're going to be at 1. So we're going to get this, and we're going to get this. And we know where our solutions are. Our solutions are right here, and right here. Now, how are we going to find them, right? How are we going to find them? Well, those are lines, all right? We're supposed to know how to figure out when 2 lines intersect. We know this line is y equals x plus 3. How do we know that? Well, because the absolute value of x plus 3 equals x plus 3 if x plus 3 is greater than or equal to 0. So that's one of our lines. The other one's the opposite of x plus 3. For the same reason we talked about in the very first problem. This is y equals the opposite of x plus 3. Well, we know which lines these are. This is y equals 2x plus 1. For exactly the same reason, right? The absolute value of 2x plus 1 is 2x plus 1 if yada, 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 yada. Or it's the opposite of 2x plus 1 if yada, 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 yada. This is y equals the opposite of 2x plus 1. Make sure you get that parentheses where it belongs. Well, you know how to figure out where these things intersect. You know how to do this math. You have x plus 3 and -2x plus 1. So you set them equal to each other. Move this over here, you get 3x. Move this 3 over here, right? What do you get? You move the 3 over here, it's negative, so you get -4. And you get x equals -4/3. Which, if you look at this, that's pretty close. I mean, for a quick sketch, that looks like -1 1/3. It's not unrealistic. And how do we do the other? Exactly the same. We get x plus 3, that's this line. Here we get 2x plus 1. We don't even have an opposite sign. So I'm going to bring the x over here, and that's going to give me x. I'm going to take the 1 over here, and we get 2. x equals 2. Okay. Now, I wonder if those actually work. I don't know. We should check them. If I put 2 in here, I get 5. If I put 2 in here, 2 times 2 is 4, plus 1 is 5. Wham! If I put negative 4/3 in here, oh my gosh, it's going to take so much effort. 3, by the way, is 12/3. For those of you that aren't following along at home, 3 equals 12/3. That's cute, Kev. 3 equals, apparently I'm not following along at home. 3 equals 9/3, right? 3 is 9/3. So this would be negative 4/3 plus 9/3. That would be that side. That would be 5/3, right? This would be 2 times negative 4/3, right? 2 times negative 4/3. So 2 times negative 4/3 plus 1. So that's negative 8/3 plus 3/3. That's negative 5/3. But don't forget, it's in an absolute value sign. 5/3. They do work. Multiple problem solving strategies, right? That's what Stewart's trying to get you to realize. All right, so there's some problems for you from Appendix A. What about Appendix C? Well, that's the trick, right? And I'll do a couple of these as well. I know this video is longer than you want it to be, but you don't have to watch the whole thing, right? You're just watching the video until you get to a part that you need. Hopefully you don't need it all. So let's talk about Appendix C. By the way, if you're curious, I filmed these videos in one of the upstairs bedrooms in our house. My daughter used to live in this room, but she has the audacity to have moved out. And now we have a YouTube studio up here. So that's what we do our YouTube videos. All right, so here we go with Appendix C. All right, this is trig, right? And our assignment here is 1 to 39 odd. So I'm not going to start with converting degrees to radians, radians to degrees. I'm not drawing any angles in standard position. I think we can do all those things. I'm not going to find the exact trigonometric ratios for angles. Hopefully you can find the sine and the cosine. I'll start with something like problem 13, right? Problem 13. And it says the sine of theta is 3/5. And it tells us that on top of that, theta is between 0 and pi over 2. It's inside. And now, what are they trying to tell us here? Well, this is 0 and this is pi over 2. They're trying to tell us theta is in quadrant 1. And we know what happens in quadrant 1, right? All the trig functions are positive. Now, when you get a problem like this, and again, this is a straight up pre-calc problem. You may see this on a quiz. I don't know if I'm going to be burning you with something like this on a midterm. It is, after all, calculus class. They want us to find the 6 trig functions. My advice is just to write them all down. Sine of theta, cosine of theta, tangent of theta, cosecant of theta, secant of theta, cotangent of theta. Now, why did they tell us which quadrant we're in? Well, so we know that these all get pluses. Right? If we were in a different quadrant, some of those would be positive and some of those would be negative. Right? In quadrant 2, all students, right? Students, sine and cosecant are positive. The other 4 are negative. Your tangent and cotangent are positive. The other 4 are negative. Your cosine and secant are positive. The other four are negative. So they have told us the sign. Now, our job, this gives us the sign, SIGN. Now we need to fill in the number. We know the answer here, 3/5. We know the answer for cosecant because it's the reciprocal of sine, so it's 5/3. Now, how do we find the other ones? Well, we draw the triangle. We know sine is opposite over hypotenuse. So we have a right triangle where the opposite side is 3 and the hypotenuse is 5. Well, that means if we use the Pythagorean theorem or our knowledge of 3, 4, 5 triangles, this side is 4. Now, theta is right here. How do I know that's theta? 3 is opposite. And now we just fill in the rest. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. Secant, right? Secant is hypotenuse over adjacent, or we take the reciprocal of this, whichever way you want to do it. Cotangent is adjacent over opposite. And we're done. That's what they want us to do in problem 13. What about 15? Find correct to 5 decimal places the length of the side labeled X. Okay. I have a calculator handy, but so I'm not going to be able to do the work, right? The arithmetic. But we all know how to solve right triangles. We learned how to solve right triangles. The very first time you were asked to solve right triangles was in Algebra 2. Then you solved right triangles in geometry, and then you solved right triangles again in pre-calc. So you have a triangle whose hypotenuse is 10. This angle is 35 degrees. This is 10. Sorry, the hypotenuse is 10, and this is X. Well, this is opposite, and that's hypotenuse. Opposite and hypotenuse is sine. So we know the sine of 35 degrees equals the opposite side, X, over 10. So X equals 10 times the sine of 35 degrees. And of course, I don't have a calculator, so I'm not going to be able to find that to 5 decimal places. But that's how you do 15. Right? That's how you do 15. All right, skipping down now. We get these identity questions. Now, the identity questions come down to how much do you know about the relationship between trig functions, right? How much do you know? Like they give us something like we can do 23, right? 23. It says sine of theta cotangent of theta, sine of theta cotangent of theta equals cosine of theta. Oh, this is pretty ridiculous. Now, remember how you solve identities. You work with one side, get it as simple as you can get it. If it matches the other side, great. If it doesn't, work with the other side for a while. But what you cannot do is move things across the equal sign. Can't use the rules of algebra and move things because you're trying to prove they're equal. You don't know they're equal. Now, this identity pretty much falls out, right? We know sine theta goes here. We know the definition of cotangent is cosine of theta divided by sine of theta. The signs cancel, and we get cosine theta equals cosine theta, and we're done. All right, that's how we do identities. If we skip down to questions like 27, they're testing to see if you know your identities, right? That's what's going on in 27. In 27, they ask you, what is the value, the numerical value of sine of x plus 1? Now, we know an identity for the sine of x plus 1. It's the sine of the first term, the cosine of the second term, plus the sine of the second term, the cosine of the first. All right, we're supposed to know that identity. That comes out of pre-calc. That identity is supposed to be something we know. If you look in the reading, for section or so for Appendix C. There is nothing in a box, nothing in a box in this section you don't need to know. And by know, I don't mean, oh, I'll look that up. I mean, it has to be 2 times 6 equals 12 kind of knowledge. All of these boxes are things that we were supposed to leave pre-calc, knowing and accepting as being something we weren't going to forget. Now, if we've forgotten them, that's fine. There's no sin in that. No one's going to kick you out of class or, do anything, put you on YouTube and call. No, we just learn them again. And this time we don't forget them. They're a big part of what happens in our calculus class. So there's an identity, for sine x plus y. It's right here. That's where I got what I got there. Well, I got it out of my head, but it's right here. It's identity 12a. Right? So what do they tell me? They tell me in problem 27, sine of x is 1/3, right? So these are my givens. I'll write them over here. Sine x equals 1/3. And they tell me sine of y, secant of y equals 5/4. Right? Now, these are very familiar numbers, 1 and 3, 5 and 4. They also tell us that x and y lie between 0 and pi/2. Now, we've already talked about that, right? They lie between 0 and pi/2. They're in the quadrant where all the trig functions are positive. And why is that important? Well, I know the sine of x is 1/3, so I can plug that in. It goes right here. But I also need to know what the cosine of x is. How am I going to find it? Well, I'm going to draw a triangle. Sine is opposite over hypotenuse. So I'm going to draw a triangle. The opposite side is 1. The hypotenuse is 3. Now we can use the Pythagorean theorem to find the other side, right? We can call this x if you want. But x is really this angle right here, isn't it? So let's don't use x. We'll call it a. So a squared plus 1 squared equals 3 squared. A squared equals 8. A equals 2√2. So this is 2√2. Not a. Well, now we can find the cosine of x. The cosine of x, I need it right here. Cosine of x is 2√2 over 3. That goes here. But I need the cosine of y and the sine of y. Well, they didn't tell me that. Well, they did. They told you the secant of y. So you know the cosine of y is 4/5, right? Reciprocal of secant. So cosine of y goes right here. Now I need the sine of y. What are you going to do? You're going to draw a triangle. You don't have to worry about plus and minus because after all, you're in the first quadrant. Cosine is adjacent over hypotenuse. So if this is 5, this is 4, this is y. We know that's 3. I need the sine of y. Sine of this is opposite. This is 3/5. And now we know our answer. And we can find our answer. This is going to be 4/15 plus 6√2/15, or 4 plus 6√2/15. And since you don't get a calculator on the test, I'm going to be really suspicious if you have a different answer than that. All right, so that's 27. We only have to go to 39, right? Solving trig equations. We're supposed to know how to solve trig equations. I know all these things are things we learned in pre-calc, and we may not have gotten 100% on this test. And then time went by, and then we showed up in calc, and they really expect us to know these things when we didn't necessarily know them when we were in pre-calc. That's okay, right? Now is the time we master this. So if we look at something like 31, right? 31. How do we solve this? We solve it just like we did in algebra 2. It says sine 2x equals cosine 2. Sine 2x equals cosine of x. I want a 0. I gotta have a zero. Gotta have it equal to zero. It's always gotta equal zero. If it equals zero, I'm happy. If it doesn't equal zero, I'm not happy. So how do we get it to equal zero? I'm going to cosine the other side. Now that doesn't help me. You're right. I can't factor that. Well, I can when I remember what sine 2x is. Sine 2x is 2 sine x cosine x. All right? That's our double angle identity for sine. It's one of those things in the box, right? Now we factor out a cosine. Now we're back in algebra 2. Right? We're right back in algebra 2. We have something times something equals 0. When that happens in algebra 2, they said the first one is going to be 0, or the second one is going to be 0. Wish it was 2x, don't you? Instead of 2 sine x. But it's okay, we can solve these, right? These are things we know how to solve. How do we solve cosine x equals 0? Well, if we take a look at the problem, it says find all the values in the interval 0 to 2 pi. 0 to 2 pi, right? The graph of cosine goes like this. This is 2 pi. This is 0. We know where cosine is 0. 0 right here. That's pi over 2. It's 0 right here. That's 3 pi over 2. So our answer to this is x equals pi over 2, or x equals 3 pi over 2. But now we have the purple one to solve. Right now we got to solve the purple. It's okay, we can solve the purple. The purple one is 2 sine x equals 1, or sine x equals 1/2. Now we know the graph of sine. Graph of sine goes like this. 1/2's right here. This is 1, right? This is the graph of sine. This is 1. Maximum of 1. 1/2's right here. Now we know this is pi over 2. We know this is pi. We know this is 3 pi over 2. We know this is 2 pi. And why do I bring that up? Because that means this is quadrant 1. This is quadrant 2. This is quadrant 3. And this is quadrant 4. And you know, funny thing, sine is positive 1/2. And you know what? It's in quadrant 1 and quadrant 2. Of course it is. All students take calculus. The sine is positive in quadrant 1 and quadrant 2. Now what do we need? We need the angle that goes along with 1/2. All right, 1/2. How are we going to find that? Well, we could. Right? We could grab our calculator and ask our calculator when does sine equal 1/2. It's going to give us some whacked out number. Or we could just go, well, you know, sine is opposite over hypotenuse. Let's draw a triangle. The opposite side is 1, the hypotenuse is 2. We know this triangle, right? This is our 30, 60, 90 triangle. This is 1, 2, the square root of 3. This is x. How do I know it's x? Well, the opposite side is 1, and the hypotenuse is 2. That's x. Okay. Well, we know what that reference angle is. That reference angle is pi over 6. Not 30 degrees. There are no degrees in a calculus book. Once we start the calculus book, we're in the review section, the appendices. Once we get in the book, there are no degrees. Between chapter 1 and chapter 12 of this book, there are no degrees. There's only radians. So we have pi over 6. Now what do? Well, we draw reference angles. In the first quadrant, pi over 6 is pi over 6. In the second quadrant, our reference angle is pi over 6. This is pi. That's 6 pi over 6, right? Because that's 1. I mean, and over 6 is that's 6 pi over 6. We're 1 back. Well, that's 5 pi over 6. So we get x equals pi over 6, or x equals 5 pi over 6. That's how we solve trig equations. Just like that. There is no other way. This is what we do. Especially when they're nice enough to ask us only to solve them in one rotation of the unit circle. Right? That's the nice thing. Don't worry. I'm never going to ask you to do more than that. All right, so that's 31. We only have to go to 39. So let's do more, right? Let's try 37. 37 is a graphing problem, right? And how do we graph? Well, we graph using all of our rules from pre-calc. And if you don't remember your graphing rules from pre-calc, let's just review those really quick. Okay. Let's just use y equals the absolute value of x as our base graph. What can happen with that? Well, we can add a number inside. We can subtract a number inside. We can add a number outside. We can subtract a number outside. Okay. Now, we're supposed to know what each one of these does. This is a shift left. This is a shift right. This is a shift up. This is a shift down. Now, what else can happen? Well, we can multiply by a number on the outside. We can divide by a number on the outside. Okay. Now, if we multiply by a number on the outside, and the number is greater than 1, then we said in pre-calc that that's a vertical shift. Vertical. It stretches our graph vertically. So maybe you talked about it as a vertical stretch. If we do it this way, this is a vertical compression. Now, the other thing we have to worry about, right, is when we multiply inside. Those are the ones that confuse us a lot, because if we multiply inside, something like this, y equals 2x quantity squared. So we multiply inside, or y equals 1/2 x, and it's inside the function. These are horizontal shifts and compressions. The thing we had to remember here is that when the number's bigger than 1, it becomes a horizontal compression. And when the number is smaller than 1, it becomes a horizontal stretch. And that flies in the face of common sense, because we see the half and we think it's going to get smaller, but it doesn't. It actually gets bigger in the horizontal direction. So that's a stretch. Okay, this is the one we all had to try to remember when we were taking our test in pre-calc. If we take a look at problem 37, right? Let's just write that down here, right here on the bottom. We have some 37. It says y equals cosine of the quantity. Grab the cosine. I could have made that a c, but that would have been slow. X minus 1/3. It wants to draw the graph. Well, we have cosine. This is what we have, right? We're shifting to the right 1/3. Now, there's no pretty way to draw this graph, right? I mean, if you want to, what I used to teach my students was just draw yourself a cosine graph, because we're all really good at those, right? Apparently I'm not. Draw yourself a cosine graph. You have to, now this is 0, right? But if you shift the graph to the right 1/3, then that means this point moves over here 1/3, right? That point moves here. And this 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 point moves here. And so your new cosine graph, right, is this one. And then you have to label these points, right? So what is this point? Well, this is 1/3. 1, because it moved. Now, what's this point? Well, we know this coordinate here is 0. What is this? Well, it's pi over 2 plus 1/3. There's no good way to write it. We just write it like that. What's this point right here? Well, we know this is -1, and this is going to be pi, right? That was our old point right here, plus 1/3. And then this point right here, right, when it gets back up here to the top, what point is this point? Well, this point is 1 again, right, because it gets back to 1. And this is 2 pi plus 1/3. There's just no nice way to write it. So we just write it like that. That's fine. We all know what that means. All right. I hope this helps you get started with your homework. If you have questions on other problems, I'm willing to work them out during class.